All right, let's get started. Be helpful if I had my markers out. Here's our setup. These two boxes are thermally, they can't let energy escape. In this box, we have diatomic gas particles. There's 1.5 moles. The pressure is kept constant by a piston moving up and down. Energy kind of moves this way, it's solid, it's liquid. There's always some solid in this box. And in this box, the temperature is high enough to excite the rotational mode for the entire process. We're given that the initial change in energy is 4 watts, or not change in energy, flow of energy is 4 watts. The final is 1 watt. The entropy of this gas box is negative 38.9 joules per Kelvin. And we want to know what the change in entropy is for this unknown box. So let's take our bearings here. You know that pressure on that right box is constant, which means it's isobaric. So we know the delta S is equal to N times Cp times log natural of temperature final over temperature initial. So let's take stock of this. What do we know in this equation? We know delta S is negative 38.9. We know N is 1.5. We can calculate Cp. So that leaves us with a ratio for final and initial. So let's try to figure out what Cp is. Let's look at the modes. We're given that in the box it's diatomic, so that means translationally it can move one way, 2 ways, and 3 ways, right? So we have 3 translational. Rotationally, it can move this way, and it can move this way, and it can move that way. So that's 2 translational. And then that leaves us with 1 vibrational. But we have to split that into kinetic and potential, so that's 1, 1. So in total, that's 3 plus 2 plus 2, so that gives us 7 modes. To calculate Cp, that's equal to Cv plus R. Calculate Cv, that would be the number of modes, which is 7, times 1 over 2R, which is equal to 7 over 2R. Plug that over here, we get 7 over 2R plus 2 over 2R, and that's 9 over 2R. So we know that Cp here now know Cp is 9 over 2R. And then R is of course the constant, so let's isolate Tf and Ti. We get e to the power of delta S over N Cp is ln Tf over T, or no, not ln, excuse me. Where did we get there? It's equal to Tf over Ti, Ti times e to the power of delta s over n Cp is equal to Tf. And once we plug in the values we know, we get e to the power of delta s negative 38.9 times n 1.5 times 4.5 times r, constant, which is 8.314, and we get 0.49999, which we're gonna be lazy and round to 0.50, so we get Ti times 0.50 Tf. Great, let's save that somewhere. Okay, great. What do we do with that? Oh, no, it's gonna flip. That's fine. What exactly do we do with this information? Well, that's a good question. What do we do with this information? Oh, yeah, okay. So consider the fact that we know dq dt for initial and final. We know dq dt is equal to temperature hot minus temperature cold. We can make a ratio that the initial flow of energy over the final flow of energy over the initial flow of energy is equal to temperature hot minus temperature cold final over temperature hot minus temperature cold initial. Let's fill in some blanks here. We know final is 4, or no, we know final is 1, initial is 4, is equal to, what do we do with TH and TC? Well, let's look. We'll see that entropy for what we know is negative, which means heat is flowing this way. We can set this up to be for final temperature final minus temperature of what we're looking for over temperature initial minus temperature. Now let's try to get rid of some. We know that temperature final is equal to 0.5 temperature initial, so let's do that. So just right up here. There, we replace it with 0.5 temperature initial. Let's try to get rid of some terms. We're going to divide this whole side by t. 0.5 times t initial over t minus 1 over t initial over t minus 1. That cleans it up a lot. Multiply this over here, multiply 4 over here, so we get t initial over t minus 1 is equal to 4 times 0.5, which is 2 t initial over t minus 4. Add that over, so we get 3 is equal to ti over t. Now multiply over here. And now get the relationship 3t is equal to ti. Save that. Great, okay. Now, what can we do with that? Okay. Well, what's the equation for this if we know it's isothermal? V delta S, which is U, is equal to Q over T. Great. Well, let's fill in the blanks here. We just found out T is equal to, or 3T is equal to Ti, so we can rewrite this as Q times 3 over temperature initial but now we don't know Q, but we do know Q would have to be the same the whole time because it's thermally, what's the word? Thermally insulated. So we can use that isobaric equation, which would be we get delta SU is equal to 3 over Ti is Q, and that would be what on top don't we get? NCP delta T. Okay, let's try that. Q is equal to NCP delta T. Let's recall we said CP is 4.5 R. Okay, so now we get, oh, but it's negative because it's flowing there. Because if we're going to use the isobaric, we've got to account for the fact that it's losing energy, negative N CP delta T. Okay, great. So what does this do? Well, we're going to see that this Ti is going to be gone. So now we get delta SU is equal to 3 over Ti, negative N CP times T final minus T initial. Delta SU is equal to 3 over Ti, negative N CP 0.5 Ti minus Ti. Delta SU is equal to 3 over Ti, negative N CP, negative 0.5 T initial. And that comes all out too. These negatives cancel. Delta SU is equal to 3 N CP times 0.5 Ti over Ti. Cancel those Ti's. So now what do we get? We get delta SU is equal to 3 over 2 times N, 1.5 is what we're given, times 4.5 times R, which is 8.314. The math should check out because we are left with delta SU, which is this, is equal to 84 joules per Kelvin.